Right now, light is racing toward you from our nearest stellar neighbor. 4 years old. 25 trillion miles traveled. When it reaches your eyes, you are seeing 3 stars pretending to be one. A red dwarf that explodes multiple times per day, a gas giant hiding where planets cannot form. And in 2024, the James Webb Space Telescope aimed its golden mirrors at this triple system and captured an image that divided the scientific community. A planet that appeared, vanished, and left behind a mystery that could reshape our understanding of habitable worlds. If this sounds as wild to you as it does to us, hit subscribe and come along. Brace yourselves. We begin now. The light hitting your eyes right now left Alpha Centauri when Donald Trump was first running for president. Think about that for a moment. While you were scrolling through election news in 2016, photons were already racing toward Earth from the closest star system to our own. 4 years and 4 months they traveled through the absolute void of space, 25 trillion miles. That is the distance light crosses in 4.37 years, moving at 671 million miles per hour. Never slowing, never stopping, crossing emptiness so vast it makes the ocean look like a puddle. And yet this cosmic neighbor is closer to us than any other star in the entire galaxy. Astronomers measure stellar distances in parsecs, a unit so vast it makes miles seem like measuring the ocean with a teaspoon. Alpha Centauri sits 1.34 parsecs away. For perspective, most stars you see at night are hundreds or thousands of parsecs distant. We are staring at distant suns from eras, when dinosaurs walked Earth, or when our planet had not yet formed. The light from some stars began its journey before life crawled from the oceans. Alpha Centauri is practically in our backyard, but here is where the mystery deepens. Despite being our nearest stellar neighbor, Alpha Centauri moves with terrifying speed. The entire system is racing toward us at 14.5 miles per second. Every hour brings it 60,000 miles closer. Every day, 270,000 miles closer. In 29,000 years, it will reach its closest approach at just 3.26 light years. Then it will swing past us like a cosmic stranger and recede back into the dark, growing more distant with each passing millennium. Even measuring this distance required catching something almost invisible. As Earth orbits our star each year, Alpha Centauri appears to shift position against the background of more distant stars. This tiny wobble, called parallax, measures just 1.52 arcseconds. Imagine watching a quarter shift by 1.5 inches from 2.5 miles away. You would need extraordinarily precise instruments just to detect the movement. That minuscule shift, barely perceptible even with our best telescopes, allowed astronomers in the 1800s to calculate the distance for the first time, confirming what had been suspected but never proven. The numbers become even more staggering when you consider travel. If you tried driving there at highway speed, 70 miles per hour, the journey would take 41.9 million years. A commercial jet flying at 500 miles per hour would need 11 million years. Our fastest spacecraft, Voyager 1, launched in 1977 and currently traveling at 38,000 miles per hour, would arrive in 75,000 years. By then, humanity as we know it might not even exist. Civilizations would rise and fall 3,000 times over. Ice ages would come and go. Evolution would reshape every species on Earth beyond recognition. The ancient Greeks saw Alpha Centauri burning in the southern sky and named the constellation Centaurus, but they never knew it was multiple stars locked in a gravitational dance. Arab astronomers called it ridddle Centaurus, the foot of the centaur. For thousands of years, humans looked up and saw a single bright point of light, never suspecting the truth. We now know it is 3 stars pretending to be one. And in August 2024, the James Webb Space Telescope pointed its most powerful instruments at this system and detected something that should not exist. What you see with your naked eye is a lie. When you look at Alpha Centauri from the southern hemisphere, you see a single brilliant point of light, the 3rd brightest star in the night sky. Your eyes cannot resolve what is actually there. Two stars locked in an 80-year gravitational waltz, spinning around each other at distances that dwarf our solar system. And far beyond them, a third star so faint you need a telescope just to confirm it exists. This is Alpha Centauri A yellow star almost identical to our own. It weighs 1.1 times the mass of our star. It burns 52% brighter. Its surface temperature reaches 5,790 Kelvin, nearly identical to what warms Earth. If you stood on a planet orbiting Alpha Centauri A, you would see a sun so similar to ours you might forget you were 4 light-years from home. But you would never be alone in that sky. Alpha Centauri B orbits alongside it, an orange dwarf, slightly cooler and dimmer. The two stars circle each other in an elliptical dance that brings them as close as 1 billion miles and pushes them as far as 3.3 billion miles apart. That closest approach roughly matches the distance between our star and Saturn. The farthest separation equals the distance to Pluto. Their orbit takes 79.91 years to complete. Humans have watched them circle each other only 2 or 3 times since we first resolved them as separate stars in 1689. A Jesuit priest named Jean Richaud was observing a comet when he noticed something strange. The bright star he was using as a reference appeared double through his telescope. He had discovered the binary nature of our closest stellar neighbor entirely by accident. The two stars swing around a common center of gravity with an eccentricity of 0.52. This describes an orbit far more elliptical than circular, more oval than round. When they reach their closest approach, the gravitational chaos intensifies. Any planets trying to form in the region between them would be torn apart or flung into the void. And then there is Proxima. Alpha Centauri C sits 13,000 astronomical units from the main pair. Neptune orbits our star at 30 astronomical units. Proxima is 400 times farther from Alpha Centauri A and B than Neptune is from our star. The distance equals 1.2 trillion miles. Proxima takes 550,000 years to complete a single orbit around the binary pair, assuming it is even gravitationally bound at all. Some astronomers still question whether Proxima truly belongs to the system. It is a red dwarf, a tiny star weighing just 12% the mass of our star and producing 1/600th the luminosity. Its surface temperature barely reaches 3000 Kelvin, giving it a dull red glow. You cannot see it without a telescope, even though it sits slightly closer to Earth than Alpha Centauri A and B. It was discovered in 1915 by Robert Innes in South Africa, who noticed a faint red star sitting 2 degrees away from the bright binary. What makes this system stranger is what we have found. Despite being the smallest, dimmest, most violent star in the system, Proxima hosts at least 2 confirmed planets, and possibly 3. Meanwhile, the 2 bright stars that should be ideal for planet formation appear almost empty. Decades of searching have found nothing confirmed around Alpha Centauri A or B. Until August 2024, most of humanity has never seen Alpha Centauri. The star is invisible to anyone living north of latitude 29 degrees. That line cuts through Houston, Jacksonville, and the northern edge of the Sahara Desert. If you live in New York, London, Paris, Tokyo, or Beijing, Alpha Centauri never rises above your horizon. Entire civilizations have lived and died without ever glimpsing the closest star to our own. The ancient Greeks knew about it, but barely. Their astronomers in Alexandria could see it hovering just above the southern horizon on clear nights. They included it in the constellation Centaurus, the centaur, placing it at the creature's front hoof. To them, it was just another bright star in a sky full of wonders. They had no idea what they were looking at. Arab astronomers gave it the name ridddle Centaurus, the foot of the centaur. They could see it more clearly from the Arabian Peninsula and North Africa. Still, the star remained a curiosity. No one suspected it was our nearest stellar neighbor. No one knew it was 3 stars masquerading as one. The first major breakthrough came in 1689. A Jesuit priest named Jean Richaud was stationed in India, tracking a comet through his telescope. He needed a reference star to measure the comet's movement, so he aimed at the bright star in Centaurus. What he saw shocked him. The single point of light separated into two distinct stars when magnified. He had accidentally discovered that Alpha Centauri was a binary system. For 200 years, astronomers assumed these two stars were the whole story. Then, in 1839, Thomas Henderson measured the parallax from the Cape of Good Hope in South Africa. The measurement was crude by modern standards, but it revealed something extraordinary. Alpha Centauri was the closest star system to Earth. The number stunned the astronomical community. For centuries, humans had been staring at our nearest stellar neighbor without understanding what it was. But the system had one more secret. In 1915, Robert Innes was working in Johannesburg when he noticed something peculiar. A faint red star sat about 2 degrees away from the bright Alpha Centauri binary. That is 4 times the width of the full moon. Most astronomers would have dismissed it as unrelated. Innes decided to measure its proper motion, the speed at which it moves across the sky. The result changed everything. The faint red star was moving in the same direction and at nearly the same speed as the Alpha Centauri binary. This was no coincidence. The red dwarf was part of the same system, orbiting the main pair at a staggering distance of 13,000 astronomical units. Innes named it Proxima Centauri because it turned out to be slightly closer to Earth than the other two. Proxima is too faint to see without a telescope, glowing at magnitude 11.1. You would need binoculars at minimum, and even then you would struggle to spot it unless you knew exactly where to look. For all of human history until 1915, we were completely unaware that the closest star to our own was a tiny red dwarf burning in the southern sky. This geographic accident has shaped how we study the system. Nearly all major observations of Alpha Centauri have been made from the southern hemisphere. Telescopes in Chile, South Africa, and Australia have carried the burden of exploring our nearest neighbor, the Very Large Telescope, Hubble, during its southern observations. And in August 2024, the James Webb Space Telescope, which orbits far above any hemispheric limitations. What it found there has astronomers questioning everything they thought they knew. Alpha Centauri A is essentially our star's twin. The temperature of its surface reaches 5,790 Kelvin. Our star burns at 5,778 Kelvin. The difference is 12 degrees across nearly 6,000 degrees of scorching plasma. They share spectral type G, 2V, the same classification, the same color, the same stellar DNA. If you swapped one for the other, you might never notice the difference from Earth. But there is a difference, and it matters. Alpha Centauri A weighs 10% more than our star. It burns 52% brighter. Its diameter stretches 22% larger. These numbers might sound small, but in astronomy, even tiny variations can mean the difference between a planetary system and a barren void. The star is also older, somewhere between 5 and 6 billion years compared to our star's 4.6 billion years. And here is where it gets strange. Alpha Centauri A contains 70% more metals than our star. In astronomy, metals means anything heavier than hydrogen and helium. Iron, silicon, carbon, oxygen, all the elements that build planets. This star formed from a cloud enriched with debris from previous stellar generations. It had more raw material to work with. According to everything we know about planet formation, Alpha Centauri A should have more planets than our star. Metal-rich stars statistically host more gas giants. The correlation is strong and confirmed across thousands of exoplanet systems. More metals means more dust in the protoplanetary disk. More dust means larger planetesimals. Larger planetesimals means faster growth into giant planets. The math is simple. The observations back it up. High metallicity stars should be planet factories. Yet, Alpha Centauri A shows no confirmed planets. Decades of radial velocity measurements detected nothing. Transit searches found nothing. Direct imaging campaigns found nothing. For years, astronomers stared at a system that should be teeming with worlds and saw only emptiness. The absence became more puzzling the longer it persisted. Meanwhile, Proxima Centauri, a tiny red dwarf with far less metal content, hosts at least 2 confirmed planets and possibly 3. The contrast is maddening. Alpha Centauri A sits 100,000 times closer than most exoplanet host stars we study. A planet there would appear 100,000 times brighter than the same planet orbiting a star 1,000 light-years away. We could study its atmosphere in exquisite detail. We could search for biosignatures with instruments that exist right now. We could measure seasonal changes, track weather patterns, maybe even detect cities if they existed. But first, we have to find the planets. The proximity advantage makes Alpha Centauri A the perfect laboratory for answering fundamental questions. Why does our solar system have the architecture it does? Why do we have 4 rocky planets close and 4 gas giants farther out? Is this arrangement common or rare? If Alpha Centauri A has planets, how do they differ from ours? If it has none, why did our star form a planetary system while its near twin did not? These questions have haunted astronomers for decades. And then, in August 2024, the James Webb Space Telescope pointed its mid-infrared camera at Alpha Centauri A and detected a faint point of light orbiting at roughly twice the distance Earth orbits our star. A planet where no planet should exist. 50 to 75% of all stars in our galaxy are in binary or multiple star systems. Think about that number. Half or more of all the stars you see at night are actually 2 or more stars bound by gravity, circling each other in eternal dance. Binary systems are the norm. Single stars like our own are the minority. If we want to understand how planets form in the galaxy, we must understand how they form around binary stars. This makes Alpha Centauri A and B perfect targets. They are close enough to study in detail. They are similar enough to our star to make comparisons. And they are metal-rich, which according to every model should mean they formed planets. Gas giants especially. The statistics are clear. Stars with 70% more metals than our star host gas giants at significantly higher rates. Yet for decades, we found nothing. Radial velocity surveys searched for the telltale wobble that planets induce as they orbit. Nothing. Transit surveys watched for the slight dimming when a planet passes in front of its star. Nothing. Direct imaging campaigns tried to photograph planets in infrared light, filtering out the star's glare. Nothing. The silence was deafening. Proxima Centauri, by comparison, revealed its secrets easily. Radial velocity confirmed Proxima b in 2016, a potentially habitable world orbiting every 11 days. Follow-up observations suggested Proxima d in 2022, a Mars-mass planet orbiting every 5 days. The tiny red dwarf, despite being far less massive and metal-poor than Alpha Centauri A, appeared to host multiple worlds. Why would the stars similar to our own be barren while the red dwarf teemed with planets? One possibility is that binary dynamics disrupt planet formation. When 2 stars orbit each other as closely as Alpha Centauri A and B do, their gravity stirs the protoplanetary disk like a spoon in coffee. Material that should settle into planets gets flung around, ejected, or ground down. Simulations show that super-Earths and sub-Neptunes form less frequently in close binary systems, but gas giants should still form. Another possibility is that planets exist but are hiding. Rocky planets are small and faint, difficult to detect even around single stars. Around a binary system with 2 bright sources of light, the challenge multiplies. Perhaps Earth-sized worlds orbit Alpha Centauri A, but our instruments cannot see them yet. Perhaps they orbit at angles where transits never occur, and radial velocity signals get lost in stellar noise. Or perhaps something darker is happening. Perhaps the high metallicity is a trap rather than a gift. Carbon-rich stars produce carbon-rich planets. Worlds with diamond mantles and stagnant lids. Geologically dead. Unable to sustain magnetic fields, atmospheres stripped away by stellar wind, maybe Alpha Centauri's metal abundance doomed its planets before they could fully form. The mystery persisted until 2019. That year, astronomers using the Very Large Telescope's NEAR experiment detected something. A faint thermal signature orbiting Alpha Centauri A at roughly 1 astronomical unit. The signal was marginal, barely above the noise, with a signal-to-noise ratio of only 3. Most scientists remained skeptical. The detection could have been real. It could have been an artifact. Then came August 2024, and everything changed. In May and June of 2019, the Very Large Telescope in Chile attempted something never tried before. The NEAR experiment, funded by breakthrough initiatives, aimed to photograph planets around Alpha Centauri A and B using mid-infrared wavelengths. Not measure their gravitational tug, not watch them transit, actually photograph them, see them as points of light against darkness. The technical challenges were enormous. The binary nature meant dealing with 2 bright stars. The proximity, usually an advantage, became a curse because the stars moved so quickly across the sky. The team observed for 100 hours over 19 nights. They used an upgraded VisiIR instrument equipped with an annular groove phase mask coronagraph to block starlight. A deformable secondary mirror corrected for atmospheric turbulence in real time. Most ingeniously, they implemented an 8 Hz chopping technique that switched between Alpha Centauri A and B 8 times per second. Planets around A would appear as positive sources. Planets around B would appear as negative sources. Background noise would cancel out. The data volume was staggering. 5 million images, 7 terabytes. After months of analysis, the team found something. A point source designated Candidate 1, or C1, located roughly 1.1 astronomical units from Alpha Centauri A. The thermal signature suggested a giant planet with a radius between 3 and 11 Earth radii, somewhere between Neptune and Saturn in size. The signal appeared repeatedly in subsets of the data, but the signal-to-noise ratio was only 3. In astronomy, a detection typically requires a signal-to-noise ratio of at least 5 to be considered robust. 3 is marginal. It means the signal is 3 times stronger than background noise, which sounds significant until you realize how many false signals random noise can produce. Instrumental artifacts, cosmic rays, scattered light from the binary companion. All of these can mimic planetary signals. Most of the scientific community remains skeptical. The team published their findings with appropriate caution, acknowledging that C1 could be a systematic artifact rather than a real planet. They called for independent confirmation. The detection was intriguing, they said, but far from conclusive. The astronomical community largely agreed. Some dismissed it entirely. Others filed it away as interesting but unverified. The signal sat in limbo for 5 years. No follow-up observations confirmed it. No other telescope attempted verification. The NEAR experiment had been a one-time campaign, and reproducing those observations with different instruments proved difficult. The chopping technique was novel and powerful but complex. C1 remained a ghost in the data, tantalizing but unproven. Then in August 2024, the James Webb Space Telescope turned toward Alpha Centauri A. JWST used a completely different instrument, a different wavelength, a different technique, orbiting in space rather than on the ground. The team was not trying to confirm the 2019 detection. They were conducting their own independent search using the most powerful infrared telescope ever built. What they found was on the opposite side of the star from where C1 had been detected. 5 years had passed between observations. If a planet orbited Alpha Centauri A on an approximately 2 to 3 year orbit, it would have completed 1.5 to 2.5 orbits in that time. It would now be on the opposite side of the star. The position matched. The brightness matched. The thermal emission matched. Suddenly, the 2019 detection nobody believed looked credible. Imagine trying to spot a firefly hovering next to a searchlight from 25 trillion miles away. That is the challenge of direct imaging around Alpha Centauri. The stars are blindingly bright. Any planet orbiting them would be millions of times fainter. The light from the star drowns out the faint glow from the planet like a spotlight drowns out a candle. Traditional coronagraphs can block most of the starlight, creating a dark region around the star where planets might become visible. But in a binary system, you have two searchlights instead of one. The Very Large Telescope team needed something radical. They invented a technique called binary chopping. 8 times per second, a motorized mirror flipped the telescope's view back and forth between Alpha Centauri A and Alpha Centauri B. The detector captured images alternating between the two stars so rapidly that atmospheric conditions remained essentially constant between frames. This created something remarkable. Planets around Alpha Centauri A would appear as positive sources in the A frames and vanish in the B frames. Planets around Alpha Centauri B would appear as positive sources in the B frames and vanish in the A frames. Background objects, instrumental artifacts, and scattered starlight would appear in both sets of frames with similar brightness. By subtracting the B frames from the A frames, everything that appeared in both images cancelled out. Only the planets remained. The technique was elegant, powerful, and extraordinarily difficult to implement. It required split-second timing, perfect atmospheric correction, and sophisticated algorithms to align and subtract thousands of images without introducing new artifacts. The telescope also needed a deformable secondary mirror. Atmospheric turbulence distorts starlight as it passes through Earth's air, making stars twinkle and blurring images. Adaptive optics systems measure these distortions in real time and deform a flexible mirror to compensate, essentially untwinkling the stars. The Visier instrument on the Very Large Telescope used a deformable secondary mirror with hundreds of actuators that adjusted shape thousands of times per second. Without this mirror, the chopping technique would have failed. The 8 Hz chopping rate was deliberate, slower, and atmospheric conditions would change between A and B frames, breaking the cancellation faster, and the mechanical systems could not keep up. 8 Hz was the sweet spot where the atmosphere stayed stable and the hardware could function reliably. Each observation session involved thousands of chops, millions of individual frames, all of which had to be perfectly aligned and subtracted. The data processing took months. Astronomers had to identify and remove cosmic rays that struck the detector during exposures. They had to correct for slight misalignments between frames caused by mechanical imperfections in the chopping mirror. They had to model and subtract residual starlight that leaked past the coronagraph. They had to distinguish real point sources from statistical fluctuations in the background noise. When the analysis finally finished, they had Candidate 1, a faint point source sitting at roughly 1 astronomical unit from Alpha Centauri A. Signal-to-noise ratio of 3, marginal but tantalizing. The team published their results with appropriate caution. Independent confirmation was needed. The technique had worked, but was the detection real or just noise? 5 years later, the James Webb Space Telescope provided the answer using completely different methods in space. 4.24 light-years from Earth, a planet circles a red dwarf star every 11 days. Proxima b was confirmed in August 2016 after years of radial velocity measurements. The discovery made headlines around the world. The closest potentially habitable exoplanet to Earth, a world you could theoretically reach within a human lifetime if we could build spacecraft fast enough. A place where liquid water might exist on the surface. The numbers seemed almost too perfect. Proxima b weighs at least 1.17 times the mass of Earth. It orbits at 0.0485 astronomical units from Proxima Centauri, which sounds incredibly close until you remember that Proxima is a red dwarf producing only 1/600th the luminosity of our star. At that distance, Proxima b receives roughly the same amount of energy from its star that Earth receives from ours. It sits right in the middle of the habitable zone. The habitable zone is the region around a star where temperatures allow liquid water to exist on a planet's surface. Too close, and water boils away. Too far, and it freezes solid. Proxima b orbits at exactly the distance where water could remain liquid, assuming the planet has an atmosphere and the right surface conditions. But reality is far more complicated than orbital mechanics. Proxima Centauri is not a gentle star like our own. It is an M-dwarf, a type of star that makes up 75% of all stars in the galaxy, yet might be terrible for hosting life. Proxima's surface churns with violent magnetic activity. Superflares erupt regularly, sometimes increasing the star's brightness by a factor of 10 or 20 in mere seconds. These flares blast the surrounding space with radiation at levels that would sterilize Earth's surface in hours. The planet receives 400 times more X-ray radiation than Earth. Proxima b also faces another problem. It is almost certainly tidally locked. When a planet orbits close to its star, tidal forces from the star's gravity gradually slow the planet's rotation until one face permanently points toward the star. The same physics that locked our moon to always show Earth the same face has likely locked Proxima b to always show Proxima the same hemisphere. One side of the planet experiences eternal day, the other eternal night. On the day side, the star hangs motionless in the sky, beating down with unrelenting radiation. Temperatures soar. Any water present would evaporate rapidly. On the night side, darkness reigns forever. Temperatures plunge far below freezing. Water becomes ice. The terminator, the boundary between day and night, might harbor a thin, habitable strip where temperatures remain moderate, but only if the planet has an atmosphere. Without an atmosphere to redistribute heat, the day side would be an oven, and the night side a freezer, with no temperate zone between. With an atmosphere, global wind patterns could carry heat from day to night, creating more uniform temperature across the surface. The question is whether Proxima b could retain an atmosphere given the intense radiation and stellar wind. Some models suggest the atmosphere would have been stripped away billions of years ago. Other models suggest that if Proxima b formed with enough water and has a strong magnetic field to deflect stellar wind, it might still retain a thick atmosphere. The truth is, we do not know. We have never directly observed Proxima b. We have never measured its atmosphere or detected any signs of water or life. We only know it exists because of the tiny wobble it induces in its star. Imagine a world where the same sky never changes. On one hemisphere of Proxima b, Proxima Centauri hangs frozen in the same position forever. It never rises, it never sets. It simply burns there like a malevolent eye, bathing half the planet in endless radiation. The landscape beneath experiences a single infinite day that has lasted for billions of years and will continue for billions more. On the opposite hemisphere, stars wheel overhead in eternal night. Proxima never appears above the horizon. The sky shows only distant points of other stars, including Alpha Centauri A and B, burning bright enough to cast faint shadows. Ground temperature plunges to hundreds of degrees below freezing. Any atmosphere that flows to this side freezes solid and falls as snow. Mountains of frozen nitrogen, glaciers of carbon dioxide ice, oceans turn to stone. Between these extremes lies the terminator zone, a narrow band of eternal twilight where the star sits permanently on the horizon. Temperatures here might be moderate enough for liquid water to exist, assuming the planet has liquid water at all. This strip could be the only habitable region on the entire world, a thin ring where life, if it exists, clings to survival in the dim red glow of a star that never moves. Tidal locking is inevitable for planets orbiting red dwarfs this closely. The gravitational interaction between Proxima and Proxima b creates tidal bulges on the planet. As the planet rotates, these bulges move across its surface, generating friction that dissipates energy and slows rotation. Over millions of years, the rotation slows until orbital period matches rotational period. The planet becomes locked, showing the same face to its star forever. Our moon underwent the same process billions of years ago. Earth's gravity tidally locked the Moon, so we always see the same lunar hemisphere. Proxima b, orbiting far closer to its star with much stronger tidal forces, locked even faster. The process likely completed within the first few 100 million years of the planet's existence. This creates a problem for life as we know it. On Earth, the day-night cycle drives atmospheric circulation. Sunlight heats the day side, creating rising air that flows toward the night side where it cools and descends. This global circulation distributes heat and moisture around the planet. Without this cycle, Earth's climate would be radically different, possibly uninhabitable. Proxima b has no day-night cycle. It has only day and night, separated by a terminator. Computer simulations suggest that if Proxima b has a thick enough atmosphere, global wind patterns could still develop. Hot air rising on the day side would flow high toward the night side, cool, descend, and return along the surface. This circulation could redistribute heat efficiently enough to prevent the night side from freezing completely and the day side from becoming a baking desert. But this only works if the planet has an atmosphere. If stellar wind and radiation have stripped the atmosphere away, Proxima b would be an airless rock with extreme temperature differences between hemispheres. No redistribution of heat, no liquid water, no possibility of life. Just a dead world spinning slowly through space, one face scorched and the other frozen. We do not know which scenario is correct. We have no direct observations of Proxima b's atmosphere. We have no measurements of its temperature or surface conditions. We only have the planet's mass and orbit. Everything else is speculation. And those models paint a troubling picture for tidally locked worlds. In August 2024, the James Webb Space Telescope achieved something that should have been impossible. After a failed attempt in August 2023 due to target acquisition failures, jwst successfully pointed its mid-infrared instrument at Alpha Centauri A. The challenge was staggering. Alpha Centauri moves across the sky so quickly that the telescope's pointing system had to be completely reprogrammed. The operations team wrote custom observing sequences just for this one target. The telescope used a 4-quadrant phase mass coronagraph to block the star's light. Even with the coronagraph, residual starlight flooded the detector. Alpha Centauri b, sitting 8 arcseconds away, added its own scattered light. The team had to observe a reference star, Epsilon Muscae, to model and subtract contamination from both stars. The data processing took months of careful work, removing artifacts, correcting for the system's rapid motion, building sophisticated models of scattered light. When the analysis finally finished, they found it. A faint point source sitting roughly 2 astronomical units from Alpha Centauri A. The object, designated S1, glowed at 3.5 millijansky at 15.5 microns. It was 10,000 times fainter than the star. The thermal signature suggested a gas giant, something in the range of Saturn's mass, with a temperature around 225 Kelvin. The planet was orbiting through Alpha Centauri A's habitable zone. This was extraordinary. First, it would be the closest directly imaged exoplanet to its host star ever detected. Second, it would be orbiting in the habitable zone of a sun-like star, something never before photographed. Third, its temperature and age made it the most similar to our solar system's gas giants of any directly imaged planet. But the team remained cautious. Direct imaging is notorious for false positives. Instrumental artifacts can mimic planetary signals. Scattered starlight can create ghost images. Background stars can appear to orbit if they happen to align with the target. The team needed confirmation. They needed to see the planet again in a different position, proving it was orbiting Alpha Centauri A. They scheduled follow-up observations for February 2025. When February came, they pointed jwst back at Alpha Centauri A. Same instrument, same coronagraph, same careful processing. They looked at the exact spot where S1 should be if it were on a circular orbit. Nothing. They looked again in April 2025 using Precious Director's discretionary time. emergency telescope time reserved for critical, unexpected observations. Still nothing. The planet had vanished. One of the most significant astronomical discoveries of the decade had disappeared. Aniket Sanghi, the PhD student leading the analysis, faced a choice. Either the August detection had been a false positive, an artifact that fooled even careful analysis, or the planet was real but hiding, somewhere too close to the star for the coronagraph to separate them. Computer simulations offered a tantalizing possibility. If the planet orbited on an eccentric path, tilted significantly relative to Alpha Centauri A and B's orbital plane, it would periodically swing close to the star and become invisible. 52% of stable orbits consistent with the August detection would place the planet too close to detect in February and April. The planet was not gone. It was playing hide and seek with the most powerful telescope humans had ever built. Imagine trying to spot a firefly hovering next to a searchlight from 25 trillion miles away. That was the challenge facing jwst engineers when they pointed the telescope at Alpha Centauri A. The problem was not just the overwhelming brightness of one star, but two. Alpha Centauri B, though 8 arcseconds away during the August 2024 observations, flooded the detector with enough scattered light to drown out any planetary signal. The team needed a reference star to calibrate against, so they selected Epsilon Muscae. They built custom software to model how light from both stars scattered across the instrument. Then they subtracted it pixel by pixel, frame by frame. The proper motion made everything worse. Alpha Centauri moves 3.7 arcseconds per year across our sky, faster than almost any star we observe. JWST had to track this motion in real time using Gaia catalog stars, maintaining pointing precision down to 1.5 milliarcseconds. Think of it like photographing a hummingbird in flight from across a football field while riding a roller coaster. Then the spacecraft roll maneuvers failed. The original plan required rotating JWST to different angles, which would reveal whether detected sources were real planets or just instrument artifacts. When those rotations did not execute properly in August, the team had no way to distinguish genuine signals from noise through the usual method. They had to develop alternative analysis techniques, running statistical comparisons across detector patterns, and relying on the February and April observations to rule out false positives. Dr. Charles Beichmann described it best. Incredibly challenging observations. JWST was designed to find the most distant galaxies in the universe, not to stare at blindingly bright nearby stars. The operations team at the Space Telescope Science Institute had to write entirely new observing sequences just for this one target. They pushed the coronagraph to its absolute limit, blocking starlight 10,000 times brighter than the signal they hunted. What emerged from all that custom code and painstaking calibration was a single point of light, 3.5 millijansky at 15.5 microns, a contrast ratio of 5.5 times 10 to the negative fifth power. In simple terms, the planet was over 10,000 times fainter than the star, sitting just 2 astronomical units away. But here is what haunts astronomers. If the planet moves even slightly closer during its orbit, it vanishes completely into the coronagraph's inner working angle. The instrument cannot separate star and planet when they are too close together, so the window to see this world opens and closes with orbital mechanics we still do not fully understand. August 2026 will tell us if we truly saw a planet, or if the universe played a trick on our most sophisticated telescope. When you lose a planet twice, you start questioning everything. February 2025. JWST turned back toward Alpha Centauri A, this time using director's discretionary time. That is emergency telescope time, reserved for discoveries urgent enough to interrupt the entire observing schedule. Astronomers do not request it lightly. The stakes were clear: confirm or refute the August detection before someone else claimed the telescope time for good. The images came back, empty. Where S1 had glowed in August, there was nothing but background noise. No thermal signature, no point source, just the star and its scattered halo of light. April brought a second attempt. Still nothing. Aniket Sanghi, the Caltech doctoral student leading the analysis, summed it up with careful understatement. We are faced with the case of a disappearing planet. Some colleagues whispered that S1 had never been real. Maybe it was a systematic error, a ghost in the data processing pipeline. Maybe the August detection resulted from imperfect subtraction of Alpha Centauri B's scattered light. Maybe they had spent millions of dollars and precious telescope time chasing an artifact, but Sanghi and his team did not give up. They turned to computer simulations instead, modeling millions of potential orbits to see which ones fit all three observations: visible in August 2024, invisible in February, invisible in April. The simulations required massive computing power. Each orbit had to be tested for dynamical stability under the gravitational influence of Alpha Centauri B, which tugs on anything orbiting Alpha Centauri A. The results surprised everyone. 52% of stable orbits placed the planet too close to the star during February and April for JWST's coronagraph to detect it. The planet had not vanished. It had simply moved into the blinding glare where our instruments go blind. Think of it like watching a moth circle a streetlight. Sometimes it flies far enough away that you can see it clearly. Other times it passes right in front of the bulb and disappears into the brightness. The moth is still there. You just cannot resolve it anymore. Orbital mechanics suggested the planet swings between 1 and 2 astronomical units from its star on an elliptical path with an eccentricity around 0.4. When it reaches periastron, the closest approach, JWST loses it completely. When it swings back out to apostron, it reappears like a cosmic game of hide and seek. The universe had not taken the planet away. It had just hidden it in plain sight. But we would get one more chance to find it. 5 years is a long time in astronomy, but sometimes it is exactly the right amount of time. Back in May and June 2019, the Very Large Telescope ran an experiment called NEAR, hunting for planets around Alpha Centauri, using a technique no one had tried before. The team found a candidate they labeled C1, glowing faintly about 1.1 astronomical units from the star. The signal-to-noise ratio hovered around 3, marginal enough that most astronomers filed it away as interesting but unconfirmed. Without independent verification, C1 remained a question mark in the data. Then JWST found S1 in August 2024. Different telescope, different instrument, different wavelength, same star. And when researchers plotted both detections on an orbital diagram, something remarkable emerged. The two signals sat on opposite sides of Alpha Centauri A. Dr. Kevin Wagner from the University of Arizona put it simply: when you see a dot of the same brightness several years later on the opposite side of the star, the story becomes much more compelling. The time separation matched perfectly with an orbital period between 2 and 3 years. If you ran the simulations forward from C1 in 2019, the planet should have completed either 1.5 orbits or 2.5 orbits by August 2024. Both scenarios placed it almost exactly where JWST found S1. The team simulated millions of orbits connecting the two detections. 52% of dynamically stable solutions fit both observations while also explaining why the planet disappeared in February and April 2025. The orbital parameters clustering around the most likely solutions suggested a semi-major axis between 1.6 and 2.1 astronomical units, with moderate eccentricity around 0.4. 4 distinct orbital families emerged from the analysis. 2 were prograde, meaning the planet orbits in the same direction as Alpha Centauri B circles Alpha Centauri A. 2 were retrograde, orbiting backward. Half the solutions favored 50 degrees of inclination. The other half favored 130 degrees, which is really the same orbit viewed from the opposite angle. What made this connection so powerful was the independence of the observations. VLT and JWST use completely different instruments, different observing techniques, different wavelengths. Any systematic error affecting one telescope should not appear in the other, yet both found thermal emission at nearly identical brightness levels, separated by 5 years and 180 degrees of orbital arc. 2 data points do not prove an orbit, but 2 data points from completely independent telescopes, separated by half a decade, fitting the same family of elliptical paths. That starts to look less like coincidence and more like the universe showing us something real. August 2026 will be the tiebreaker. The planet was not missing, it was dancing. Computer models revealed that S1 follows a wildly elliptical orbit, swinging from 2 astronomical units out to less than 1 astronomical unit, then back again every 2 to 3 years. At a postron, when it reaches maximum distance from Alpha Centauri A, jwst can see it clearly. At periastron, when it plunges inward, the planet crosses inside the inner working angle of the coronagraph and vanishes completely into the stellar glare. The eccentricity hovers around 0.4. For comparison, Earth's orbit is nearly circular with an eccentricity of just 0.017. Even Mars, considered fairly elliptical in our neighborhood, manages only 0.09. An eccentricity of 0.4 means this planet experiences dramatically different temperatures and radiation levels depending on where it sits in its orbit. But the eccentricity itself is not constant. Alpha Centauri B, orbiting 12 to 36 astronomical units away from Alpha Centauri A, exerts a gravitational torque on anything circling its companion star. This triggers what astronomers call von Zippel-Kozai-Ledoff oscillations. The planet's eccentricity and inclination trade places over thousands of years. When the inclination drops, the eccentricity surges. When the inclination rises, the eccentricity falls. Computer simulations suggest the eccentricity could spike as high as 0.8 during extreme phases, creating an orbit so elongated the planet would graze dangerously close to its star before being flung back out. The inclination adds another layer of chaos. Most planets in binary systems align roughly with the binary orbital plane, keeping mutual inclinations below 30 degrees. S1 appears tilted at either 50 degrees or 130 degrees relative to the Alpha Centauri AB plane. That is steeply inclined, suggesting this world either formed in a tilted disk or underwent violent gravitational scattering sometime in its past. Think of the planet like a ball on a string being swung in wild circles. Sometimes it flies far out where everyone can see it. Sometimes it whips close to the center and blurs into motion too fast to track. The string itself twists and wobbles because a second person stands nearby, tugging on the whole system. The next visible window opens in August 2026. Orbital simulations predict the planet will be near a postron then, separated far enough from the star for jwst's coronagraph to resolve it. If it appears where the models say it should, confidence jumps above 95%. If it does not, we go back to the drawing board. The universe rarely makes things easy, but it always leaves clues if you know where to look. If this planet is real, it sits in one of the strangest places imaginable. The habitable zone around Alpha Centauri A stretches from 0.9 to 1.3 astronomical units, the region where liquid water could exist on a rocky planet's surface. S1 orbits right through this zone, swinging between 1 and 2 astronomical units, depending on where it sits in its eccentric orbit. For part of each cycle, this world passes through the exact distance where life might thrive, except life cannot thrive there, because the planet itself is a gas giant. With a radius between 1.0 and 1.1 times Jupiter's size, and a mass somewhere between 90 and 150 Earth masses, S1 falls squarely in the Saturn range. It has no solid surface to stand on, no ground for liquid water to pool. The temperature averages around 225 Kelvin, cold enough to freeze carbon dioxide, but warm enough to keep methane gaseous. The atmosphere likely churns with ammonia clouds, methane hazes, and vast storm systems driven by the planet's internal heat and the varying radiation it receives during its elliptical orbit. But here is where it gets interesting. Gas giants can host moons, large ones. Saturn has Titan, with its thick nitrogen atmosphere and methane lakes. Jupiter has Europa, with its subsurface ocean warmed by tidal flexing. If S1 has moons anywhere near that size, they could be habitable. The planet's eccentric orbit would generate enormous tidal forces on any satellites, kneading their interiors and releasing heat through friction. That tidal heating could keep subsurface oceans liquid even at distances where solar radiation alone would freeze everything solid. Aniket Sanghi captured the significance. If confirmed, this would mark a new milestone for exoplanet imaging efforts. Of all the directly imaged planets, this would be the closest to its star seen so far. It is also the most similar in temperature and age to the giant planets in our solar system, and nearest to our home Earth. The planet's very existence challenges our understanding of how worlds form and survive in binary systems. Alpha Centauri B orbits close enough to disrupt planet formation around Alpha Centauri A. Computer simulations show that giant planets in such systems either form quickly before the binary's gravity tears the disk apart, or they migrate inward from farther out. S1 probably formed beyond the snowline, where water ice could condense, then either stayed put or drifted slightly inward over billions of years. Its presence raises an uncomfortable question. If a Saturn-mass giant orbits through the habitable zone, what happened to any Earth-like planets that might have formed there? Gas giants do not coexist peacefully with rocky worlds. Their gravity acts like a bowling ball rolling through pins, scattering smaller planets into chaotic orbits or flinging them out of the system entirely. The closest potentially habitable world might also be the reason no habitable world can exist there at all. Sometimes the most important discoveries are the things you do not find. When jwst observed Alpha Centauri A, it achieved something unprecedented. It measured exozodiacal dust levels with sensitivity 10 times better than any previous star. Exozodiacal dust is the cosmic equivalent of the faint glow you see along the ecliptic before dawn, caused by sunlight scattering off tiny particles left behind by comets and asteroids. Every planetary system should have at least some of this dust. Collisions never stop completely. Comets still break apart. Asteroids still grind into powder. JWST found almost none. The upper limit came in at less than 5 to 8 times the dust level in our own zodiacal cloud. That might sound like a lot, but most stars similar to our parent star have significantly more dust than this. Some have hundreds of times more. Alpha Centauri A is remarkably, almost suspiciously clean. Dr. Max Sommer from the Cambridge Institute of Astronomy described the significance. This observation shows how deeply Webb can probe the dust environment of the nearest similar stars. We can now explore exozodiacal dust at levels not much higher than those in our own solar system, tapping into a whole new way of looking at other star systems. The low dust level tells us several things. First, the system is either very old and has already cleared out most of its planetesimals, or it never had much debris to begin with. Second, if S1 exists, it likely swept its orbital zone clean over billions of years. Gas giants act like cosmic vacuum cleaners. Their gravity stirs up asteroid belts and comet clouds, sending debris either into the star or out of the system entirely. Simulations show that if S1 is real, any debris disk around Alpha Centauri A could only survive inside 0.4 astronomical units, too close to the star for JWST to detect. Third, the lack of dust makes future searches for rocky planets much easier. Dust scatters starlight and creates false signals that can mimic or hide planetary signatures. A clean system is a searchable system. When the next generation of telescopes comes online, the Extremely Large Telescope in the late 2020s and the Habitable Worlds Observatory in the 2040s, they will have a clear view. No dust clouds to confuse the data, no debris belts to comb through, just planets, if they exist. But the cleanliness also raises a troubling possibility. Maybe the reason Alpha Centauri A has so little dust is because it has so few planets. Planet formation creates debris. Collisions between protoplanets leave rubble. Gravitational stirring kicks comets into star-crossing orbits. A system with low dust might be a system that never built many worlds in the first place. Or maybe a giant planet already destroyed them all, and we are looking at the aftermath. Either way, the silence speaks volumes. What we do not see can reveal just as much as what we do. Alpha Centauri A has a secret written in its starlight, and that secret might doom any worlds orbiting there. Spectroscopic analysis reveals that both Alpha Centauri A and B contain about 60% more metals than our parent star. Metals, in astronomical terms, means anything heavier than helium: iron, silicon, oxygen, carbon. More metals should mean more planets, because planets form from the dust and gas in protoplanetary disks, and metal-rich disks build worlds faster and more efficiently. So why does Alpha Centauri seem relatively planet-poor? The answer might lie in what kind of metals dominate. If the carbon-to-oxygen ratio is elevated, and measurements suggest it might be, then any rocky planets forming there would be carbon-rich rather than silicate-rich like Earth. That fundamentally changes what those worlds are made of. Instead of an iron core surrounded by a silicate mantle, you get a diamond or silicon carbide core surrounded by graphite and carbide rock. Dr. Haiyang Wang from the University of Arizona ran models showing that such a planet would be more geologically dead due to diamond's increased thermal conductivity and viscosity. Diamond conducts heat 5 times better than silicate rock. That means heat from the core reaches the surface much faster, allowing the planet to cool and solidify into a thick, immobile crust. Earth stays geologically active because heat trapped in the mantle keeps rock viscous enough to flow. Convection currents drive plate tectonics. Plates subduct, volcanoes erupt, carbon cycles between atmosphere and crust. A carbon-rich planet loses its internal heat too quickly. The mantle freezes solid. Plate tectonics never start or shut down early in the planet's history. Alpha Centauri also has 25% fewer heat-producing radioisotopes than our star system. Uranium, thorium, potassium, the elements that decay slowly over billions of years and keep planetary interiors warm. With less radiogenic heating and higher thermal conductivity, any rocky worlds around Alpha Centauri A would go geologically dead faster than Earth did. A dead planet cannot regulate its climate. On Earth, the carbon cycle works like a thermostat. When the atmosphere gets too hot, more rain falls. Rain weathers rocks into carbonates. Carbonates subduct at plate boundaries and eventually release carbon dioxide back through volcanism. Too cold? Less rain, less weathering. Carbon dioxide builds up and warms the planet again. No plate tectonics means no carbon cycle. Carbon dioxide dissolves in rain, weathers into carbonates, and stays locked in the crust forever. The atmosphere loses its greenhouse gases, the planet freezes, or alternatively, if the planet starts with too much carbon dioxide and no way to remove it, it bakes into a runaway greenhouse like Venus. A world made of diamond sounds like something from a fairy tale. Mountains of crystal glittering under an alien star. But beauty without geology is just a frozen museum, no volcanoes, no earthquakes, no magnetic field to shield against stellar radiation. The wrong chemistry can trap a planet in eternal stillness, no matter how perfect its distance from the star. If S1 exists, it is not just occupying the habitable zone, it is destroying it. Gas giants and rocky planets do not share space peacefully. A Saturn-mass planet orbiting through the habitable zone exerts gravitational influence over everything nearby. Its gravity creates resonances, regions where orbital periods sync up in simple ratios like 2:1 or 3:2. Any smaller planet wandering into a resonance gets kicked into a more elliptical orbit. Over millions of years, those eccentricities grow until the orbit crosses another planet's path. Collision or ejection follows. Think of it like a bowling ball rolling through pins. The ball does not have to hit every pin directly. The first few pins scatter sideways and knock down the rest. S1 would act the same way. Even if it never directly approached a rocky planet, its gravitational perturbations would destabilize everything in the surrounding region. Computer simulations of planetary systems in binary stars show that super-Earth and sub-Neptune formation is suppressed when the binary separation falls below 100 astronomical units. Alpha Centauri A and B orbit between 11 and 36 astronomical units apart. That is well within the suppression zone. Any rocky planets trying to form around Alpha Centauri A would face constant gravitational harassment from Alpha Centauri B, tugging from one side and S1 tugging from the other. The likely outcome? Either no terrestrial planets formed at all in the habitable zone, or they formed and got scattered long ago. Some might have been flung into the star. Others could have been ejected into interstellar space, lonely wanderers with no star to orbit. A few might have been pushed outward into colder, more distant orbits where they froze solid. There is one alternative scenario: moons. If S1 has large satellites, those moons orbit the planet rather than the star, protected by the planet's gravitational dominance. The planet's eccentric orbit would generate tidal heating through constant flexing and kneading of the moon's interior. That heat could maintain subsurface oceans even when the moon passes through the coldest parts of the orbit. Saturn has Titan, Jupiter has Europa and Ganymede. All three have more water than Earth does, locked under ice or dissolved in thick atmospheres. If S1 hosts similar satellites, they could be habitable despite orbiting a gas giant. We have no way to detect exomoons yet. They are too small, too faint, too close to their parent planets, but the physics allows them to exist. So the habitable zone around Alpha Centauri A might not be empty. It might just be inhabited by the wrong kind of world. A gas giant where rocky planets should be, moons instead of planets. A cosmic bowling alley where the pins got knocked down billions of years ago. The places where life should emerge are often the places where life never got the chance. Imagine a world where continents are made of diamond and mountains glitter with silicon carbide under a golden star. It sounds beautiful. It sounds like something from science fiction, and it would be completely, utterly dead. Diamond is one of the hardest materials in the universe, which is exactly the problem. Hard materials do not flow, they do not convect. They do not participate in the slow churning that keeps planets geologically alive. On Earth, the mantle behaves like an extremely viscous fluid. Heat from the core creates convection currents. Hot rock rises, cool rock sinks. This convection drives plate tectonics at the surface. Plates spread apart at mid-ocean ridges. They collide and subduct at trenches. Volcanoes erupt. Earthquakes shake the ground. A carbon-rich planet with a diamond mantle would have none of that. Diamond's viscosity is so high that mantle convection would slow to a crawl or stop entirely. The crust would freeze into a single, thick shell. Geologists call this a stagnant lid. Mars has one. Venus probably has one. Mercury definitely has one. None of those worlds have plate tectonics. None have a way to recycle material between surface and interior. The thermal conductivity makes everything worse. Diamond conducts heat 5 times better than silicate rock. Heat escapes from the core into space much faster than it does on Earth. The planet cools and solidifies into a rigid ball within a few billion years, maybe less. Once the mantle freezes, volcanism shuts down. No more outgassing, no more replenishment of the atmosphere. Without plate tectonics, there is no carbon cycle. Carbon dioxide dissolves in rain. Rain weathers rocks into carbonates. Carbonates stay on the surface forever, with no subduction to carry them back down. The atmosphere loses carbon dioxide. Without greenhouse gases, the planet freezes. Unless it started with a thick carbon dioxide atmosphere, in which case it bakes like Venus because nothing removes the excess. No mantle convection means no magnetic dynamo. Earth's magnetic field comes from liquid iron churning in the outer core. That convection generates electric currents, and those currents create the magnetic field that shields us from solar wind. A stagnant lid planet has no convection, no dynamo, no magnetic field. Stellar wind strips the atmosphere away over billions of years. Alpha Centauri A has 25% fewer heat-producing radioisotopes than our parent star. Uranium, thorium, potassium, the elements that keep interiors warm through radioactive decay. Start with less internal heat, lose it faster through higher thermal conductivity, and you get a planet that dies young. A world made of diamond would sparkle brilliantly from space. No clouds to obscure the view, no plate boundaries creating topography, just smooth, crystalline surfaces reflecting starlight. It would be a monument to stillness, a museum of what could have been if only the chemistry had been different. The most beautiful planets might also be the most hostile to life. Beauty and habitability do not always coincide. Sometimes the universe builds wonders that can never wake up. The question haunted planetary scientists for decades. If most rocky exoplanets have stagnant lids, are we alone by default? Earth is unusual. Most rocky bodies in our neighborhood, Mars, Venus, Mercury, have thick, immobile crusts. No plate tectonics, no carbon cycle. If that is the norm rather than the exception, and if carbon cycles are required for long-term habitability, then Earth-like worlds might be vanishingly rare. But recent computer models suggest the answer is more nuanced. Researchers led by Dr. Nicola Tosi at the DLR Berlin Institute ran simulations coupling interior evolution, volcanic outgassing, and climate feedbacks. They found that under specific conditions, stagnant lid planets can maintain habitable surface conditions for billions of years. The key is volcanic outgassing during the first few billion years of the planet's life. Even without plate tectonics, partial melting in the upper mantle can release water and carbon dioxide through volcanism. If the planet starts with the right amount of water in its mantle, between 34 and 1,000 parts per million, and the right oxygen fugacity, a measure of how oxidized the rock is, then outgassing can build a stable atmosphere. The habitable zone for stagnant lid planets is narrower than for plate tectonic worlds. It depends on how much carbon dioxide gets outgassed. Too little and the planet freezes. Too much, and you get a runaway greenhouse with surface pressures exceeding 100 bars of carbon dioxide. Hot enough to boil water even at high pressure. But there is a sweet spot. If the outgassing rate is just right, surface temperatures stabilize between the freezing and boiling points of water. The problem is duration. Volcanism on stagnant lid planets shuts down after a few billion years as the interior cools and solidifies. Once volcanism stops, there is no way to replenish the atmosphere. Carbon dioxide gets locked into carbonates. Water gets lost to space or trapped in minerals. The planet enters a terminal freeze. Tosi and colleagues concluded that stagnant lid planets can be habitable over geological timescales, but joint modeling of interior evolution, volcanic outgassing, and accompanying climate is necessary to robustly characterize planetary habitability. Translation: it is possible, but the window is narrow and the conditions are strict. For Alpha Centauri, the prospects look grim. 25% fewer radioisotopes means less internal heat. Higher carbon content means higher thermal conductivity. Both factors push toward faster cooling and earlier cessation of volcanism. Any stagnant lid world around Alpha Centauri A would have a shorter habitable window than a similar planet around a star with solar composition. But shorter does not mean zero. Life on Earth emerged within the first billion years. If the same timescale applies elsewhere, a stagnant lid planet around Alpha Centauri could host life for 2 or 3 billion years before freezing permanently. That is enough time for microbes. Maybe even enough for simple multicellular organisms. Not enough for intelligence to evolve, probably. Not enough for civilizations. The universe might be full of worlds that came alive and then fell silent. Planets that had their chance and lost it when their interiors froze solid. Fossils of biospheres locked in stone, waiting for someone to dig them up and ask what could have been. Sometimes the saddest possibility is not that life never existed. It is that life existed and then ended, leaving no one behind to remember. Proxima Centauri should be calm by now. 4.8 billion years old, nearly the same age as our solar system, this tiny red dwarf has had eons to settle into peaceful middle age. Stars like these burn slowly, living trillions of years, their hydrogen fuels stretched across timescales that dwarf the entire history of the universe so far. You would think, after nearly 5 billion orbits around the galactic core, that Proxima might finally relax. You would be catastrophically wrong. This star is a monster wearing the mask of tranquility. The magnetic field tells the story first. 600 Gauss, maybe 750 on bad days. Our own star manages about 1. Proxima's field is 600 times stronger, coiled and twisted like steel cables under impossible tension. These magnetic loops snake through the stellar atmosphere, storing energy the way a drawn bow stores violence. When they snap, they release that fury all at once. We call these events superflares. The name fails to capture the terror. During one recorded event in March 2017, Proxima brightened by a factor of 1,000 in just 10 seconds. Imagine standing on a planet where your star suddenly becomes 1,000 times brighter than usual. The sky would go from twilight to nuclear white in the time it takes to exhale. 10 seconds. That is how long the universe gave any hypothetical observer to realize their world was ending. These superflares happen multiple times per day. Some are smaller, merely doubling or tripling the star's output. The big ones, the civilization enders, arrive less frequently, perhaps once per month, perhaps once per week. The statistics are still emerging, and each new study reveals worse news than the last. The energy released during a major flare can reach 10 to the 38th ergs. That number means nothing until you compare it to our star's most violent outbursts. Proxima's routine tantrums release 10 to 100 times more energy than our star manages during its worst behavior. Proxima b receives 400 times the X-ray dose that Earth gets. 400 times. And that is just the baseline, the everyday radiation environment when the star is behaving itself. During flares, that number spikes higher. The ultraviolet flux sits at 30 times Earth's exposure, even during the quiet periods. If you could somehow stand on Proxima b with a UV meter during a calm day, the device would scream warnings that would send every Earth organism scrambling for shelter. The flares bring friends. Coronal mass ejections, vast bubbles of magnetized plasma, erupt from the stellar surface and race outward at millions of miles per hour. When they slam into a planet, they do not simply deliver radiation. They physically strip away atmospheric particles, molecule by molecule, layer by layer. They peel the sky like removing paint from a wall. For 4.8 billion years, this has been happening. Every day, every week, every month, relentless. Proxima b, sitting just 4.5 million miles from this violence, has endured nearly 5 billion years of cosmic assault. The planet completes 32 orbits in the time Earth completes one. 32 passes through the firing range every single year we count. Multiply that across billions of years and you arrive at a number too large to comprehend. This is the closest potentially habitable world to Earth, our nearest neighbor in the habitable zone, the planet that science fiction writers dreamed about for decades before we confirmed its existence. And it orbits a star that makes our own solar weather look like a gentle spring rain. The star wears its age well, burning bright and violent, a red dwarf that refuses to grow old gracefully. What survives 4.8 billion years of that? The flares are only the beginning. Behind each burst of light and radiation comes something worse. The stellar wind from Proxima Centauri flows 500 to 2,000 times stronger than the gentle breeze that streams from our own star. Think of it as a hurricane compared to a whisper. This wind carries charged particles, protons and electrons that slam into anything in their path at hundreds of miles per second. When they hit a planetary atmosphere, they do not bounce off, they dig in. The process has a clinical name: atmospheric erosion. The reality is far less sterile. Imagine standing on a beach as waves crash against a sandcastle. Each wave removes a little more sand, grain by grain, until nothing remains but a memory of what stood there. Proxima b has been standing in that cosmic surf for nearly 5 billion years. Scientists ran the calculations. They built computer models of what happens when a planet sits this close to a star this violent with a stellar wind this strong. The results came back measured in oceans. 21 Earth-ocean equivalents of water could be lost to space over the lifetime of the system. 21 entire oceans, each one as deep and vast as the Pacific, the Atlantic, the Indian combined. All of it stripped away, molecule by molecule. Hydrogen ripped from oxygen, the lighter element escaping into the void while the heavier one stays behind. Nitrogen does not fare better. Models suggest up to 100 bar of nitrogen atmosphere could vanish through a process called ion pickup. The stellar wind's magnetic field acts like a comb dragging through the upper atmosphere, snagging ions and accelerating them to escape velocity. Bar by bar, year by year, the air itself bleeds into space. The planet may have had everything it needed at the beginning: water, atmosphere, the right temperature, all the ingredients for life as we understand it. Then came 4.8 billion years of exposure to stellar violence. The early years were worse. Young red dwarfs burn hotter and flare more frequently than their older selves. Proxima spent its first 169 million years much more luminous than today. During that time, any water on the surface would have boiled. Scientists call this a runaway greenhouse phase. 3 to 10 ocean equivalents likely vanished during just that initial period. What remains today sits in the crosshairs of ongoing bombardment. Without a magnetic field, the atmosphere has no shield. Earth's magnetic field deflects most of the solar wind around our planet, creating a protective bubble called the magnetosphere. Proxima b might not have that luxury. Tidal locking could suppress the dynamo that generates planetary magnetic fields. No rotation, no liquid metal core churning in the right way, no field, no protection. The star does not care whether you are ready. It does not wait for evolution to catch up or for chemistry to build defenses. It simply strips away everything it can reach, photon by photon, particle by particle, atmosphere by atmosphere. We see the scars in our own solar system. Mars lost most of its air billions of years ago when its magnetic field failed. Venus may have lost oceans worth of water. Even Earth sheds atmosphere at the edges, though slowly, protected by our field and distance from the star. Proxima b sits 8 times closer to its star than Mercury sits to ours. And Proxima is 600 times more magnetically active. The math is brutal, the physics unforgiving. If the planet started with everything, it may have nothing left now. If it started with nothing, the stellar wind ensures it stays that way. The erosion machine runs continuously, never sleeping, never pausing, never showing mercy to the world locked in its grip. Somewhere in the data, hidden in the noise of measurements and models, lies the answer to whether anything survived, whether survival was even possible. Ultraviolet light destroys ozone. This is not a mystery. On Earth, we know the chemistry intimately. Ozone molecules, 3 oxygen atoms bound together, absorb UV radiation and break apart. Normally, the atmosphere rebuilds the shield as fast as it degrades. Balance maintained, life protected, the sky remains a functional barrier between the surface and the lethal frequencies of starlight. Proxima b does not get to maintain balance. Each superflare from Proxima Centauri blasts the planet with UV radiation that shreds ozone molecules by the billions. The atmospheric chemistry shifts violently. Ozone concentrations plummet. The protective layer thins. UV light, no longer absorbed in the upper atmosphere, penetrates deeper. It reaches the surface where life, if any exists, would be trying to survive. Then comes the recovery period. On Earth, after a solar flare, the ozone layer rebuilds itself over days or weeks. Chemistry works its magic. Oxygen molecules split, recombine, form ozone again. The shield restores itself. Life continues oblivious to how close it came to exposure. On Proxima b, recovery never completes. The next superflare arrives before the ozone finishes reforming. Then another, multiple flares per day during active periods. The atmosphere exists in a permanent state of damage control, trying desperately to rebuild a shield that keeps getting torn down. It is like trying to build a house during a hurricane. You might get a few boards nailed together before the next gust rips them away. Studies modeled what this means over decades and centuries. The ozone layer never reaches full strength. It hovers at some depleted fraction of what a healthy atmosphere maintains. That fraction determines how much UV reaches the surface, how much mutation pressure any biological molecules face, how deep into water or soil life must hide to avoid sterilization. Years pass between the largest flares, years where the ozone might, theoretically, recover to something approaching safety. Then a major event hits and resets everything. The chemistry starts over. Any organisms that ventured into the newly protected zones get hit with the full force of stellar UV. Natural selection in overdrive. Extinction events on repeat. Earth life took billions of years to develop UV resistance. Some organisms manage it well, others die quickly under UV exposure. On Proxima b, the selection pressure would be relentless and total. Either you evolve to handle UV levels that would cook most Earth life, or you go extinct. There is no middle ground, no safe period to recover and diversify. The star dictates the terms. Deep water offers some protection. UV penetrates only the top layers of oceans. Below a few meters, life might persist regardless of what happens in the atmosphere. Subsurface environments, caves, cracks in bedrock, anywhere shielded from direct starlight, these become the only refuges. Life on such a world would not colonize the surface. It would cower beneath it. Even then, chemistry has limits. Water shields you from UV, but does nothing against X-rays, which penetrate deeper. Go deep enough to escape X-rays, and you face new problems. No light, no photosynthesis, no easy energy source. Life would have to find alternatives. Thermal vents, perhaps. Chemical gradients. Radioactive decay. The menu of options shrinks with each constraint you add. The ozone that never recovers becomes a metaphor for the planet itself, a world that cannot catch its breath, that never gets a break from the assault. That exists in permanent crisis, where the baseline condition is disaster and the flares are merely worse disasters stacked on top. Scientists debate whether such a world can host life at all. The debates continue because we lack definitive proof either way. But the ozone layer does not care about our debates. It just keeps breaking. Red dwarfs make up 75% of all stars in the galaxy. Let that sink in. 3 out of every 4 stars you see, if you could see the faint ones invisible to the naked eye, are red dwarfs. They are the universe's most common product. Small, cool, efficient, burning their hydrogen fuel so slowly that they will outlive every other stellar type by orders of magnitude. Trillions of years from now, when stars like ours have long since burned out and died, red dwarfs will still be shining. They should be the best places to look for life. Longevity means more time for life to evolve. Abundance means more opportunities. The habitable zones sit close to the star, making planets easier to detect and study. Everything about red dwarfs suggests they should be teeming with inhabited worlds. The statistics favor them overwhelming. Except for one problem, they are violent. Proxima Centauri is not an outlier, it is typical. Most red dwarfs flare. Most generate magnetic fields far stronger than our star. Most produce stellar winds that dwarf the gentle breeze we experience. The activity levels vary, but the pattern holds. Red dwarfs are magnetically active throughout their lives. Unlike larger stars that calm down with age, red dwarfs remain restless. Tidal locking becomes inevitable at these distances. A planet in the habitable zone orbits so close that gravitational forces lock its rotation to its orbit. One face permanently toward the star, one face permanently away. The day side might be habitable in temperature terms. The night side freezes. The terminator zone between them becomes the only region where liquid water might persist. But tidal locking may suppress magnetic dynamos. Earth's magnetic field arises from our rotation and the churning of liquid iron in our core. Lock the rotation and the dynamo may fail. No field means no protection from stellar wind. The atmosphere erodes, the planet dies. Even if the planet maintains a magnetic field, even if the atmosphere survives, Life faces a fundamental problem. The flares never stop. Billions of years of stellar violence, ozone layers that never fully recover, UV and X-ray radiation that would sterilize Earth's surface in days. The odds stack higher and higher against biology finding a foothold. Some scientists argue life might adapt. Evolution is creative. Given enough time and pressure, organisms could develop extreme UV resistance, thick protective shells, subsurface habitats. Life on Earth survives in boiling acid, in radioactive waste, in the crushing pressure of deep ocean trenches. Perhaps life around red dwarfs simply looks different than we imagine. Other scientists point to the statistics. We have no evidence of life anywhere except Earth. 0 confirmed detections despite decades of searching. If 3/4 of all stars are hostile to life, and the remaining quarter is dominated by short-lived, massive stars and binary systems, where exactly is life supposed to arise? The galaxy might be far more sterile than we assumed. The paradox cuts deep. The most common stars in the universe may be the least habitable. The places where planets are easiest to find and study may be the places least likely to host biology. We are biased by our own existence. We evolved around a star that represents only a small fraction of stellar types. What if we are the exception, not the rule? This matters beyond academic debates. It reshapes how we calculate the odds of finding life elsewhere. Drake equation estimates assume habitable planets are common. If M dwarfs are excluded, the number of habitable worlds drops dramatically. The galaxy could contain trillions of planets and still be mostly empty of life. Proxima b sits in the habitable zone. It ticks the box for temperature. But temperature is one variable among dozens. Stellar activity, atmospheric retention, magnetic field strength, tidal locking effects, flare frequency, radiation environment. Each variable adds a filter. Each filter removes more candidates. By the time you apply every constraint, the list of truly habitable worlds may be vanishingly small. 3 out of 4 stars eliminated for violence. Most of the rest eliminated for other reasons. What remains? Perhaps a universe far lonelier than we hoped. We define the habitable zone using temperature. The calculation is elegant. Take a star's luminosity, calculate the distance at which a planet receives enough energy to maintain liquid water on its surface, and you have the boundaries. Too close and water boils away. Too far and it freezes solid. Inside those boundaries, life as we understand it might arise. The formula fits on a single line. Proxima b sits dead center in that zone. Perfect placement. By the textbook definition, this planet occupies one of the best locations in our cosmic neighborhood for habitability. The temperature works out to roughly 234 Kelvin, cold by Earth standards but acceptable. With the right atmosphere, greenhouse warming could bring the surface to comfortable levels. Everything adds up until you add the other factors. Then the calculation collapses. Temperature is necessary for habitability, but nowhere near sufficient. A planet needs atmosphere, and not just any atmosphere. It needs the right mix of gases in the right proportions. Too little and the surface freezes despite being in the warm zone. Too much and runaway greenhouse effects turn the world into a pressure cooker. The balance is delicate. Proxima b faces stellar wind 500 to 2,000 times stronger than Earth experiences. That wind strips atmosphere continuously. Whatever gases the planet started with are under constant assault. Add in the flares, the radiation, the magnetic field interactions, and the rate of atmospheric loss accelerates. The planet might be completely airless by now. All the temperature calculations assume atmosphere exists. Remove that assumption, and the habitable zone concept breaks down entirely. Tidal locking creates its own problems. Even if atmosphere survives, even if it redistributes heat from day side to night side through global circulation, you still face a world where half the surface never sees starlight. Photosynthesis becomes impossible on the night side. The terminator zone, where day meets night, becomes the only region where conditions might allow Earth-like biology. The habitable zone shrinks from a sphere to a narrow ring. Ozone depletion adds another constraint. The habitable zone calculation assumes UV radiation stays within tolerable limits. On Proxima b, the UV flux during quiet periods already exceeds Earth levels by 30 times. During flares, it spikes far higher. Life needs shielding, or it needs to hide. The surface becomes hostile regardless of temperature. Scientists who study habitability are starting to use different terms. The classical habitable zone, based on temperature alone, is too optimistic. They propose a continuously habitable zone that accounts for stellar activity, atmospheric retention, and long-term stability. This zone is much smaller. For red dwarfs like Proxima, it may not exist at all. One of the Discovery team leads said the arguments against habitability are not proved definitive. This is technically true. We do not have direct measurements of Proxima b's atmosphere or surface. We cannot say with absolute certainty that life is impossible there. Absence of evidence is not evidence of absence. But the evidence we do have points in one direction. Every new study reveals another obstacle. Every model adds another reason why life would struggle. The weight of negative factors grows heavier. At some point, the burden of proof shifts. The question becomes not whether the planet is habitable, but whether habitability means anything at all in such an environment. We wanted our nearest neighbor to be welcoming. We wanted the closest potentially habitable world to actually be habitable. The universe does not care what we want. It operates by physics and chemistry, indifferent to our hopes. Proxima b may be in the habitable zone by temperature. By every other measure, it sits in a killing field. The distinction matters. We will spend decades studying this world, analyzing its atmosphere if it has one, searching for biosignatures if they exist. The effort is justified because proximity makes it possible, but the habitable zone that encompasses Proxima b may be a habitable zone in name only. A mathematical artifact, a cruel joke the cosmos plays on those of us who search for life beyond Earth. Stephen Hawking stood before the cameras in April 2016 and announced humanity would go to the stars. Not someday, not in the distant future when we solve all the engineering problems. Now, within a generation, he and Russian billionaire Yuri Milner unveiled breakthrough Starshot, a $100 million project to send spacecraft to Alpha Centauri at 20% the speed of light. The probes would arrive in 20 years. Your children could see images from another star system. The announcement landed like lightning. The physics are brutal and beautiful. Accelerate a spacecraft to 134 million miles per hour. Cover 25 trillion miles in 2 decades. Do it with technology we can build today, not fantasy engines from science fiction. The only way to achieve this is to make the spacecraft impossibly small and push it with light. Enter the nanocraft, 1 gram, the mass of a paperclip. Inside that gram you fit cameras, navigation sensors, power supply, communication laser, computer chips. Everything a traditional space probe carries, miniaturized to the point where mass becomes almost irrelevant. The entire payload weighs less than a sugar packet. The light sail does the impossible part. 4 meters on each side, made of silicon nitride, just 200 nanometers thick, riddled with billions of tiny holes in a pattern optimized by neural networks. The holes make the sail reflective instead of transparent. 99% of laser light bounces off rather than passing through. That 1% difference determines whether the mission works. A ground-based laser array, 1 square kilometer in size, 100 gigawatts of power, fires at the sail for 10 minutes. 10 minutes of continuous acceleration at forces up to 10,000 G. The acceleration would pulverize any human. The nanocraft, with no moving parts and nothing to break, survives. At the end of those 10 minutes, the probe is moving at 20% light speed. The laser shuts off. The probe coasts the rest of the way. 20 years later, it reaches Alpha Centauri. The flyby lasts minutes. No way to slow down, no fuel to brake. The probe screams past the star system at 134 million miles per hour, cameras recording everything possible in the brief window of observation. Then it continues into deep space, leaving the system behind forever. 4 years later, we receive the first signals. The data transmission crawls across 25 trillion miles at the speed of light. Images, spectra, measurements, everything the probe recorded during its flyby. A child born when the mission launched would be 24 years old when the first pictures arrive. Old enough to have children of their own, old enough to have forgotten the world cared about this mission. The technical challenges are staggering. Keeping the sails centered on the laser beam during acceleration requires metagratings that passively adjust the angle. Surviving impacts with interstellar dust at relativistic speeds requires materials we are still developing. Communicating from 4 light-years away with a laser powered by the probe's tiny solar panels requires the same kilometer-scale laser array that launched it to act as receiver. Yuri Milner put up the initial funding. Stephen Hawking lent his name and authority. The project assembled teams of scientists and engineers to assess feasibility. They spent years studying materials, testing components, building prototypes, running simulations. The conclusion: possible, difficult, expensive, requiring international cooperation and sustained funding across decades, but possible. Not science fiction, not fantasy. A legitimate engineering challenge with solutions visible on the horizon. The first phase concluded in 2025, $100 million spent on feasibility studies. The results are being written up. The project is on pause, while organizers seek funding for Phase 2. That phase would cost billions. Building a prototype laser array, testing full-scale sails, proving the technology works before committing to the final mission. No guarantee the money arrives, no guarantee Phase 2 ever happens. Breakthrough starshot could remain a beautiful idea that never leaves the page. But for one brief moment in April 2016, standing next to one of the greatest scientific minds of our generation, humanity announced its intention to reach another star. The dream may be impossible. Then again, 50 years ago, landing on the moon was impossible too. The light sail was always the bottleneck. You need a sail 4 meters square, lighter than a feather, reflective enough to bounce 99% of laser light, strong enough to survive 10 minutes of acceleration at 10,000 G. The material must be perfect. One defect, one weak point, and the sail tears apart under the laser's force. Building one sail using previous techniques would take 15 years and cost over 200 billion euros. The economics destroyed the entire mission concept before it left the planning stage. Then, in 2025, a team led by Norte demonstrated something extraordinary. They built a full-scale light sail in one day using optical lithography. Not a prototype, not a test section. A complete sail, 4 meters by 4 meters, with all the required properties. The cost dropped to 25 million euros per sail, a 9,000-fold reduction in price, a 15-year timeline compressed to 24 hours. The technique is deceptively simple in concept, nightmarish in execution. Optical lithography uses light to pattern materials. The semiconductor industry relies on it to make computer chips. Norte's team adapted the process to create a silicon nitride membrane just 200 nanometers thick, punctured with billions of nanoscale holes arranged in a pentagonal lattice. The holes are the secret. Light hitting a solid material either reflects, refracts, or gets absorbed. Most of the energy becomes heat. Heat destroys the sail. The holes create a photonic crystal that reflects light through destructive interference. 99% of laser energy bounces off. The remaining 1% spreads across the entire sail structure. The temperature stays manageable. The sail survives. Neural networks optimize the hole pattern. The shape is not circular, not square, not any regular geometry. Each hole is potato-shaped, sized and positioned to maximize reflectivity while minimizing mass. The pattern repeats across billions of holes. Perfect repetition across 4 square meters. One error ruins the entire structure. Previous attempts used electron beam lithography. This technique writes patterns one spot at a time, like drawing with a very fine pen. Accurate but impossibly slow. 15 years to complete one sail. The breakthrough came from switching to optical lithography, which patterns entire sections simultaneously using light masks. What took 15 years now takes 1 day. The cost reduction changes everything. 25 million euros is expensive, but not prohibitive. A billionaire could fund a single sail. A small nation could fund several. A consortium of governments could fund a full mission with multiple probes for insurance against failure. The economics shift from impossible to merely difficult. Mass production becomes conceivable. Build 1 sail per day, and you have dozens ready within months. Hundreds within a year. Launch them in sequence toward different targets. Alpha Centauri first, then Barnard's star, then other nearby systems. Spread the missions across multiple destinations. Increase the odds of success. The announcement in 2025 received less attention than it deserved. No celebrities present, no primetime press conference, just a research paper demonstrating the technique and the cost analysis. The science community understood the implications immediately. Breakthrough starshot, paused after Phase 1, suddenly became economically plausible. Questions remain. The sail survives in laboratory conditions, but can it survive launch into space? Can it deploy properly in orbit? Can it maintain integrity during 10 minutes of laser acceleration? Can it handle impacts with interstellar dust at 20% light speed? Each question requires testing. Each test requires funding. The path from laboratory to launchpad spans years or decades. Proving the technology works on paper is step 1. Building flight hardware is step 2. Testing in space is step 3. Achieving the full mission is step 4. The process cannot be rushed. Space is unforgiving. One overlooked problem destroys the mission. But the bottleneck broke. The impossible cost became merely expensive. The 15-year fabrication timeline became 1 day. Breakthrough starshot remains on pause. But the pause is no longer permanent. Somewhere in the funding discussions, in the meetings between governments and billionaires, in the calculations of cost versus scientific return, a decision will be made: continue or cancel, commit or walk away. For now, the light sails sit in the laboratory, gossamer thin, barely visible when viewed edge-on, waiting for humanity to decide whether we are serious about reaching the stars or whether we just like talking about it. 20 years sounds manageable. Launch a probe today and it arrives at Alpha Centauri when your children are in college. Wait 4 more years for the signal to return and you are still young enough to see the data. 24 years total, less than a human lifetime. Barely longer than the Voyager missions have been flying, achievable within a single generation's attention span. But 20 years is just the beginning of the complexity. The laser fires for 10 minutes, accelerating the nanocraft from stationary to 20% light speed. Those 10 minutes require the largest laser array ever constructed, 100 gigawatts of power, 1 square kilometer of focusing optics, all firing in perfect synchronization. The coordination must be flawless. One laser out of phase, and the sail tears. The spacecraft experiences 10,000 g of acceleration. 10,000 times Earth's gravity, a human would be crushed to paste instantly. Even the hardened electronics must be built to withstand forces that would shatter conventional spacecraft. Every component must be solid state, no moving parts, no liquids, no joints or connections that could fail. The entire probe is essentially a single piece of engineered material with embedded sensors and chips. After 10 minutes, the acceleration ends. The probe is moving at 134 million miles per hour. It has already traveled 1 million kilometers. The laser shuts off. From here, the journey becomes pure ballistic flight. 20 years of coasting through the void with no course corrections possible, no fuel to adjust trajectory, no way to slow down at the destination. The nanocraft must aim perfectly from the beginning. Engineers must calculate where Alpha Centauri will be 20 years from now, accounting for the star's proper motion, accounting for Earth's position in its orbit, accounting for gravitational effects from everything in between. Launch trajectory determines everything. Miss by a fraction of a degree at launch, and you miss the target by trillions of miles at arrival. Interstellar space is not empty. Dust grains, hydrogen atoms, cosmic rays, all of it hits the probe at relativistic speeds. At 20% light speed, even a grain of sand hits with the energy of a bullet. The sail must be robust enough to survive multiple impacts. The electronics must be shielded. Redundancy is impossible at 1 gram mass. You get one chance. Communication across 25 trillion miles requires a miracle of engineering. The probe carries a tiny laser, powered by solar panels, that only work when near a star. At Alpha Centauri, during the brief minutes of flyby, the probe must orient correctly, power up its laser, and begin transmitting data toward Earth. 4 years later, we receive the signal. The kilometer-scale laser array that launched the probe must reconfigure to act as a receiver. The incoming signal is unimaginably faint. Photons that left Alpha Centauri crossed 4 light-years of space, arriving 1 or 2 at a time, scattered across the detector. Advanced signal processing extracts the data from the noise. The images build slowly, pixel by pixel, as the transmission continues. A child born at launch grows up hearing about the mission. They attend elementary school while the probe crosses the first few light years. They graduate high school when it reaches the halfway point. They finish college, perhaps start a career, maybe have children of their own, and then the signal arrives. They are 24 years old. The mission that launched when they were born finally delivers its first results. This assumes everything works. One component fails, and the mission fails. One calculation error, and the probe misses Alpha Centauri entirely, sailing past into eternal darkness with no way to correct course. The probe has minutes to observe, photograph, record, and transmit during flyby. No second chances, no orbits, no lingering for detailed study, just a sprint past the target at 134 million miles per hour. Scientists joke that the probe's flyby will be over faster than the time it took to write the grant proposals that funded the mission. 20 years of travel, 4 years of signal propagation, 24 years of anticipation and waiting, all for a few minutes of data collection from another star system. But those few minutes would rewrite our understanding of our place in the cosmos. Images of Alpha Centauri's planets, if they exist, spectroscopic data revealing their atmospheres, confirmation of habitability or proof of sterility, answers to questions we have asked since we first looked up at the stars and wondered if we are alone. 24 years, 1 generation's patience, for a glimpse of another world. The next observation window opens in August 2026. This is not a guess. Orbital simulations, running through millions of possible trajectories for the vanishing planet, converge on a prediction. If the planet exists, if it follows the orbit suggested by the 2019 and 2024 detections, it will be visible again 14 months from now. Visible means separated far enough from Alpha Centauri A that the coronagraph can distinguish star from planet, far enough that the signal emerges from the glare. The simulations are confident. 52% of stable orbital solutions place the planet in a detectable position during the August 2026 observation. 52%, barely better than a coin flip, but better than random chance. The planet plays hide-and-seek on an eccentric orbit, swinging close to the star where instruments cannot reach, then swinging far where it reappears. August is the reappearance window. James Webb will point toward Alpha Centauri again. Same instrument, same coronagraph, same wavelength. The team will execute the same careful subtraction of starlight from both Alpha Centauri A and B, removing the scattered light, the diffraction patterns, the noise. They will look at the spot where models predict the planet should be. Either something appears or nothing does. If something appears at the predicted location, confidence jumps above 95%. The planet is real. The orbital solution is correct. We will have confirmed a Saturn-mass giant orbiting through the habitable zone of the nearest Sun-like star. Spectroscopy becomes the next step. Measure the atmospheric composition. Search for methane, water vapor, ammonia, whatever gases fill the atmosphere of a cold gas giant. Compare it to Jupiter, Saturn, the ice giants of our solar system. Understand how planet formation works in binary star systems. If nothing appears, we are back to the drawing board. Either the orbit model is wrong, requiring more complex trajectories to fit the data, or the 2019 and 2024 detections were artifacts, noise masquerading as signal, wishful thinking encoded in pixels. The statistical confidence collapses below 30%. The candidate becomes a cautionary tale about the difficulty of imaging planets in binary systems. Or the planet appears somewhere else, not at the predicted location, but nearby, shifted by gravitational effects we did not account for, perturbed by a planetary companion we did not know existed. This would be the most interesting outcome. It means something is there, something complicated, something that does not fit simple Keplerian orbits. A dynamically hot system with multiple bodies interacting in ways we barely understand. The team that made the initial detection is waiting. The scientists who spent years writing custom code to handle Alpha Centauri's difficult observing geometry. The researchers who ran millions of orbital simulations to predict where the planet would be. The instrument teams who maintain the telescope and schedule observations. Everyone involved is marking calendars, checking schedules, preparing. James Webb is the most requested telescope in history. Observation time is precious. Every astronomer on Earth wants to use it for their project. Allocating time to re-observe Alpha Centauri, a target already observed twice, requires justification. The scientific return must warrant the investment. The case was made. The time was granted. August 2026 is not just another observation. It is the confirmation or refutation of one of the most significant exoplanet discoveries in decades. The closest cold gas giant to Earth, if it exists. A planet in the habitable zone of a sun twin, if the data is real. A chance to understand planetary systems in binaries, if the interpretation is correct, or it is nothing. A false positive. A ghost in the data that vanished when scrutinized. Science has seen this before. Detections that could not be confirmed. Signals that disappeared. Excitement that turned to disappointment. The field learns from failures as much as successes, but failures sting differently. The telescope will observe. The data will arrive. Analysis will take weeks or months. Peer review will take longer. Eventually, a paper will be published announcing the results. Either the planet is confirmed, or it is not. Either we found something extraordinary, or we found a lesson about the limits of our instruments. August 2026, 14 months away. The moment of truth approaches whether we are ready for it or not. We have always looked toward Alpha Centauri and imagined the closest star system, 270,000 times farther than our own star, yet 100,000 times closer than most worlds we study. Close enough that if you drove at highway speed, you would arrive in only 42 million years, impossibly distant and tantalizingly near all at once. The paradox has haunted us since we first understood what stars are. Every telescope we have ever built eventually turns toward those 2 points of light in the southern sky. Optical telescopes, radio arrays, infrared satellites, X-ray observatories. We point our instruments at Alpha Centauri not because we expect to find anything specific, but because it is there. Because proximity demands investigation. Because if we cannot understand our nearest neighbors, what hope do we have of understanding anything farther? The search has consumed decades. The Very Large Telescope spent 100 hours in 2019 hunting for planets, pushing the limits of ground-based imaging. James Webb spent its precious observation time in 2024, then again in 2025, sacrificing opportunities to observe distant galaxies in favor of our cosmic next-door neighbor. The Nancy Grace Roman Space Telescope, launching 2027, lists Alpha Centauri among its primary targets. The extremely large telescope, still under construction, has dedicated observation programs planned for its first light. We cannot stop looking because we cannot accept not knowing. The question of whether planets orbit Alpha Centauri A and B is not academic curiosity. It is fundamental to understanding planet formation, stellar system architecture, the frequency of habitable worlds. If metal-rich, sun-like stars in binaries lack planets, it means something profound about the conditions required for planetary systems to form. If they have planets, it tells us binaries are not the hostile environments we feared. Science fiction writers placed civilizations at Alpha Centauri for generations before we had technology to search for planets there. The novels, the films, the games, all imagined thriving worlds orbiting those stars. Avatar put Pandora in the system. Countless other stories did the same, not because astronomers told them to, but because the human mind cannot resist populating the nearest stars with life. We are storytelling creatures. We see the lights in the sky, and we imagine neighbors. The reality is colder and more beautiful than fiction. Proxima b might be tidally locked, atmosphere stripped, surface irradiated beyond tolerance. Alpha Centauri A might host a gas giant on an eccentric orbit that cleared out every rocky planet. Alpha Centauri B might be entirely barren. None of this diminishes the wonder of knowing. Empty worlds teach us as much as inhabited ones. If we confirm the planet in August 2026, we will have achieved something previous generations dreamed about: a directly imaged exoplanet around the nearest sun-like star. We will measure its atmosphere, calculate its mass precisely, understand its orbit, compare it to our own solar system. The data will fill textbooks, dissertations will be written, models will be refined, our understanding will deepen. If we find nothing, we will have learned the limits of detection. We will know what is not there. We will refine our methods and try again with future telescopes. The search will continue because proximity makes it worthwhile. But beyond the data, beyond the measurements and models and peer-reviewed papers, there is something else, something harder to quantify. The simple fact that we built telescopes powerful enough to see planets around other stars, that we refuse to accept ignorance about our neighbors, that we spend billions of dollars and decades of effort to answer questions that do not feed us, do not shelter us, do not make us wealthier or safer. We search because we are human, because curiosity is encoded in our genes as deeply as the need for food or sleep, because looking up at the night sky and wondering what is out there is part of what separates us from every other species on this planet. We alone ask these questions. We alone build the instruments to answer them. Current rockets would take 75,000 years to reach Alpha Centauri, 3,000 human generations. Every person you have ever known, their children, their grandchildren, repeated 3,000 times before the spacecraft arrives. The distance mocks our ambitions. Yet we plan missions anyway. Breakthrough starshot, fusion propulsion concepts, generation ships. We imagine the journey because imagining is what we do. Avi Loeb said Alpha Centauri offers our best opportunity to answer whether we are alone. He is right, but the answer matters less than the asking. Whether we find life or sterility, planets or emptiness, the search itself is the point. We look because we can, because proximity demands it, because our neighbor is 4.2 light-years away, and we refuse to die ignorant of what orbits there. 14 months until the next observation. Then we will know more. Then new questions will arise. The search never ends. Each answer generates 10 new questions. Each discovery reveals 10 new mysteries. And always, through all of it, we keep looking toward those two bright points of light in the southern sky, our nearest neighbors in the cosmic dark. waiting to tell us their secrets.